So today we will do the basic concepts of chemistry, students. Okay. So basic concepts of chemistry is all about introduction to chemistry. What is that we do in chemistry? So broadly speaking, what are the ways, mainly what is called chemistry about? Okay. It's all about study composition, constitution of matter, and studying the physical and chemical properties associated with matter. Okay, so when it comes to matter, you learn what is matter. What is what matter? Matter is anything that has mass and occupies space. Okay, so what are the ways you classify matter? Based on physical properties, you classify matter into solids, liquids, and gases. Right? And coming to based on chemical properties, we classify them as pure substances and impure substances. Impure substances are otherwise called as mixtures. Right? So classification, when I take solids, liquids, and gases, see here I've given a table. It's just for you've been learning years together. Okay, so how do you classify solids, liquids, and gases based on shape, volume, rigidity, all these parameters? So in terms of shape, which is, oh, come on, quickly just tell me about, how do you distinguish between solids, liquids, and gases based on these parameters? So solids will have
Definite shape.
definite shape, and gases, they don't have a shape. How about liquids? Do they have shape or not?
They have shape one.
Is it definite? Do the liquids have definite shape?
Yes, ma'am.
No. Liquids have shape is fine, but not definite. They take the shape of the container. So if you put it in a spherical container, it will take a spherical shape. If you take in a rectangular box, it will take a rectangular shape. Isn't it? So that's not a definite shape. Unlike you take any solid, so like I have its calculator, it has some shape, it's a solid. But the same thing when I take a liquid, I put it in a water. If I put it in a cylindrical container, it will take a cylindrical shape. Isn't it? So liquids don't have specific shape. They take the shape of container. Coming to gases, on the other hand, they don't have any shape. Yeah. So volume. What can you tell about volume? Do solids and liquids have volume? How about gases? Do gases have volume?
No, ma'am.
So do you mean zero volume? What is the speciality of volume of a gas? Gases will occupy available volume. That's the specific feature of a gas. Suppose that's where a gas can be confined in a 1 liter vessel, or it can be, you can transfer the gas in a 10-liter vessel also. It will occupy all the 10 liters. Are you getting it? So gases occupy available volume, whereas solids and liquids have fixed volume. Now rigidity, solids are rigid, and what do you call liquids and gases as? We call them as? There is a name given. Liquids and gases together are called as something. There's a common feature.
Fluid.
Yes, good. They are called as fluids. Whereas solids are rigid. So rigidity is high. Whereas liquids and gases will have fluidity. Interparticle space, it is least in solids, maximum in gases, and it's intermediate in between the two. Interparticle force of attraction will be maximum in solids, minimum in gases, and in between. Kinetic energy, so which has greater freedom of movement? So all these points are correlated. They go together. They have almost give the same meaning. So which will have more freedom of movement? Particles have more freedom. Wherever there is no more interparticle space, there is more freedom of movement. So which one is it? So interparticle space is maximum in gases. So freedom of movement is maximum. So kinetic energy is maximum. Can you see all these are interrelated? Okay. Then coming to kinetic energy, it's the same thing. Diffusion, rate of diffusion. Again, rate of diffusion is related to interparticle force. What is diffusion? Diffusion is intermixing of particles. So intermixing of particles will be more with more freedom of movement. So again, that's maximum and in case of gases, and it's minimum in case of solids. How about compressibility? What do you mean by the word compression? What do you do to compress?
Make it into a minimum size.
Good. That's the exact definition. Absolutely. Yes. That's brilliant. So which one can be compressed? Maximum. Solids, liquids, or gases?
Gases, ma'am.
Gases, right? So you apply pressure, and again another, see, you can differentiate in number of parameters. So gases can be compressed. So on the other hand, when I take about the pressure concept, gases can exert pressure. All that is there. Is that clear? Individually, we will study a lot in separately liquid state, solid state, and gaseous state. Is that clear? So overall, this is a comparison, right? We are making a comparison chart. So on the other hand, you classify matter based on chemical properties into pure substances and impure substances. Pure substances are substances which have same type of particles, elements and compounds. Elements will have same types of atoms of same type, right? Whereas compounds will contain what particles? They contain molecules, right? So examples of pure substances, if I take elements. So elements, there are number of elements. Already we did periodic classification of elements. So many elements are existing. But one thing very important, when it comes to elements, some elements exist in diatomic state, like hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. These, you never express them as atomic. You never write like this. They exist. They exist in the diatomic state. See, even if I take H2, what does H2 contain? Atoms of hydrogen only, right? So what's the definition of an element? Element is a substance, the simplest form of matter, which contains atoms of same type. So that's why H2, Cl2, Br2, all these are the elemental forms. So be very clear, especially when you write chemical equations, you have to keep this mind that when you say element with respect to these H2, O2, N2, F2, Br2, I2, make sure that you take the diatomic form. Don't write it in the monoatomic state. This is very, very important. Next, compounds. Compounds are formed when atoms are taken in a fixed ratio by mass. So like when I take water, it is hydrogen and oxygen are taken in a ratio of 1:8. Be careful, it's by mass, not by volume. Volume ratio of water is 2:1. Whereas mass ratio is 1:8. So when I'm saying about formation of a compound, it's the mass ratio, it's not the volume ratio. Okay. So we will see that we'll be able to relate this with the laws of chemical combination, how a compound is defined. Okay. So coming to mixtures, mixtures are impure substances. They are homogeneous, heterogeneous. So what do you mean by homogeneous? Homogeneous means they have a uniform composition. They have a uniform texture. Is it clear? In other words, the even distribution of particles. That's what you mean by uniform. That's what does homogeneity means. So mixtures are homogeneous and heterogeneous. Homogeneous mixtures, in nutshell, we can call them as solutions. You have a separate chapter of solutions. We'll do it in class 12. Okay. Entirely about solutions. A part of it we will be doing towards the end of the chapter also. The concept of solute, solvent, everything will do. And coming to heterogeneous mixtures. Heterogeneous means there's an uneven distribution of particles. Simple. So when I take sand and water, on the other hand, I mix sugar and water. Where do you see there's a uniformity? You don't see any line of boundary of separation. In which case? Is it sugar solution or a mixture of sand and water? Can you separate out sugar from water once I mix sugar and water? No. Is it clear? Why? Because sugar particles are evenly distributed. That they go one with water, you will not be able to see where is sugar present with that. That is what you mean by homogeneity. It's a uniform distribution of particles. On the other hand, when I take sand and water, clearly you can see when you add sand to water, sand will sediment. So you can clearly see distinct boundary of separation between the two. Are you getting it? So that's what is heterogeneity mean. Okay. So in heterogeneous mixtures, you have colloids and suspensions. This again, we will take it up separately. Suspension is basically sand and water is a suspension. I've given you this example. Colloids is again exclusively another chapter. I don't want to go right now into this. We will do it in class 12. This is a chapter separately, involving the concept of colloids. Okay. Just understand that. An example of colloid, maybe I can give you. Example of colloid is milk, dust, smoke. All these are examples of colloids. Okay. Clouds. All these come under the category of colloids. Okay. So having given an example, the study of, what is a category of all, whatever I've said, the examples, all that in detail we will be doing in the concept of colloids in class 12, not now. Okay. Yeah. So I do not know if you've learned this in physics also, the basic units, all that you must have learned. The 7 basic, what are the 7 basic units? Basic units are length, mass, time, electric current, temperature, mole or amount of substance, luminous intensity, and leaving these, every other will be derived units. You must have learned this in physics also, if I'm not mistaken. Everything else will be derived units. And the prefixes. What are these prefixes? These are the prefixes we use to denote any unit. See, for example, I'm writing it as, 100 or 1,000 meters. The 1,000 is taken as 10 power 3. Okay. And 10 power 3 is prefixed. We give a notation K, it's kilometer. So when I say 1,000 grams, it's kilograms, right? Got it? So same way, when I take 1 by 1,000 of something, 1 by 1,000th will be 10 power minus 3. This is called as a milli. So these, exponential, give these prefixes in the exponential form. I would suggest that in numericals, try to use the exponential form a lot. avoid using decimals. Believe me, your calculation will become very, very easy if you use exponents rather than using decimals. Put everything as a whole number and convert the decimals into exponents. The calculations also will become easy. That's the reason we are using this. Okay, so the important ones are only here. Okay, by and large, we use deci, centi, milli, micro, nano, pico, femto is very less, but you better know it. Most of the conversions will be from this range. Okay, 10 power 3 to 10 power minus 12. This is a range. Okay, mega, giga and all where you must have used in computers. Terabyte, megabyte, gigabyte, all that, right? So, but in chemistry, we often use from 10 power 3 to 10 power minus 12. So, other units of measurements, I hope you know this, students. It's very important that you are in a position to use these units, convert them. So just now I told you, nanometer, angstrom is another one. We use it in wavelengths. Is it clear? Most of them we use it in wavelengths. 1 picometer is 10 power minus 12 meter, 10 power minus 10 centimeters. These we use it often in conversions, particularly wavelength conversions. Okay. Right. So that, then volume, again volumes, mostly liter, milliliters. So this especially, meter cube and liter is something, often students go wrong. Please take care. What is the SI unit of volume? SI unit is not a liter, it is meter cube. Please take care of this. This is the area where students often commit mistake. And the standard units we use here is meter cube, liter, milliliter or centimeter cube is same. They are one and the same. Another one unit is decimeter cube. 1 decimeter cube is nothing but 1 liter. 1 decimeter cube is equal to 1 liter. This is also a conversion which we often use. So I'm just highlighting on those conversions which we often use. It's most applied. Okay. And temperature conversion, I think you know. Yes, if you're going from the board perspective, 273.15 is mandatory. You cannot skip that 15. From the board point of view, is it clear? So competitive MCQs, we can take it as 273. But boards normally, that 0.15 is mandatory. Next is pressure. Yes, pressure is something which is, having varying units. Okay, everything is important in pressure. 1 atmosphere, conversions to, millimeters of mercury, centimeters, conversion to Pascal. SI unit is Pascal. Okay, then conversion to bar and torr. All these are equally important. You cannot skip anything. Okay. So these are the main areas I want to emphasize. Rest of it are all derived. Even pressure is also derived, but pressure is often, we apply this in many numericals and many chapters. Most of the physical chemistry chapters. Okay. So this is one thing. Please make a note of this conversions, especially for pressure. Standard temperature pressure. This is again one thing. STP condition, we say. It is 0 degrees Celsius and 1 atmosphere. Okay. We say STP or NTP condition. This is something that we apply a lot. Note the condition. Okay. And rest of it, I think students, what is the conversion of time? All that you should be knowing, right? Time SI unit is seconds. I think the remaining conversion of time you've been knowing. That how many seconds is there in a minute and how many minutes make an hour, all that conversions. Yes or no? Okay, there's a question. How many seconds are there in 3 days? How many seconds are there in 3 days? Okay, let me make your job easy. Yeah. Option?
A.
Yes, right. What is the conversion? 3 days. 1 day will have how many hours? 24 hours. And 1 hour will have how many minutes? 60 into 60 seconds. Yeah. It looks so simple, but believe me, this is where, in this, it looks like you're familiar with the calculation. This is where you tend to go wrong mostly. Please check that. Yeah. Five liters equal to how many centimeter cube? Okay. Oh, no, not centimeter cube. I'll make it meter cube. Five atmospheres in pascals. Come on. A quick calculation. One liter is how many meter cube? 1 meter cube is how many liters? One meter cube is how many liters?
1,000.
1,000. So correct. So 10 power 3. My suggestion would be that try practicing using the exponential notations. Is it clear? Because that way it will become easier for you while calculating. 1,000 is correct. Now, so 1 liter is how many meter cube? Then 1 liter will be how many meter cube? Come on, students. Okay, someone is answering.
0.001.
Again, that's what I'm telling you. Try to use the exponents. Exponents. Your answer is correct. Because the more you use exponents, you will be using this a lot in numericals. Get out of the habit of using decimals and, making using big numbers. Because the next concept will be based on that only. So one meter, yeah, 10 power. 1 meter cube is 10 cube liters. So 1 liter is how much? 10 power?
Minus 3.
Minus 3, isn't it? Okay. Practice this way, students. Practice this way. I'm not saying that your answer is wrong. Because practice using, exponential notation. Okay. So now what will be 5 liters? 5 into 10 power minus 3. Don't express it as 0.005. It's correct, no doubt. But your calculation will also go fast on the exponential notation. Are you getting it? So, you multiply, then you keep searching after how many points I have to put a decimal point, after how many zeros are there. All that, you will waste time. So the best way is use exponential notation. Errors will be less in exponential notation. Is that clear? So next is, we are going to the exponential notation only, the scientific notation. So what is scientific notation is P into 10 power Q form, where P is always a single digit number. What single digit number mean? Single digit number is a number where? Come on. Is it a single digit number?
There's only one digit.
Is it a single digit number? That's what my question is. The number I have written, is it a single digit?
Yes.
Yeah. What is a single digit number? A single digit number is a number which is less than 10, right? So is this a single digit number? It is. So after one number, if you put a decimal point, after one numeral, you put a decimal point, it's a single digit number. So P should be written in such a way that after one number, you place a decimal point. That is what is P in the P into 10 power Q form. And Q will have a positive or negative power. Is that clear? So you are representing a number. So when you say the number Q is positive, that means this number is greater than or equal to, it's greater than or equal to 10. There's a mistake here. It's greater than or equal to 10. Okay. And Q value will be equal to number of digits minus 1. Number of digits minus 1. So for example, I have a number 4896. How will I express this in scientific notation?
4 into 10 to the power 3.
So 4.89. See, after one number, you place a decimal. 4.896. This is your P. P is ready now. Into 10 power Q. Q is number of digits is how much? There are 4 digits. So Q value will be 3. Is that clear? Come on, express this.
Six point 8798 4.
Right? Into 10 power
4.
4. How many digits are there in the number?
5.
5. So
Minus 1.
power will be 4. Is that clear?
Yes, ma'am.
Is it clear to everyone? So this is a way easily you can express a number in scientific notation. Suppose what is this 6.022 into 10 power 23? No, you already learned it. It's called as Avogadro number, right? So how many digits are there in Avogadro number? So this Q is number of digits minus 1, no? So how many digits are there in Avogadro number?
24
This value is 23. Yeah, there are 24 digits. See, that's the reason we are choosing the scientific notation, because most of the scientific data, they are on the extreme end, like this, having 24 digits. Or when I take like mass of electron and all, it is, very, very small, of the power 10 power minus 31. It's too small or too big. So the best way you use these numbers is put them in the scientific notation, the exponential form. See, every exponential form is not scientific notation. If it is only p into 10 power cube, where p is taken as a single digit number, then alone you call it as a scientific notation. Is that clear? Same thing with the Q negative. In Q negative, see, this is, you can do it number of ways. This is one way to, arrange it. Is it clear or understand it? So it's number of zeros after decimal plus 1. Okay. So what do I do? Take these non-zero numbers, 658. After first number, place a decimal. So this is your P ready now. Into 10 power. How many zeros are there after decimal? 2 zeros. This will become minus 3. Okay. Come on, express it. So when Q is negative, the number of zeros after decimal plus 1 will be the value of. So come on, anybody? Yeah, someone said 7 point.
819.
Good. Into 10 power
7.
minus 7.
Minus 7.
It will be negative in this case. Correct. Your evaluation is correct. The value. See, number of zeros, how many are there? 6 are there. To that, add 1. So it will be 7 and you express it as minus 7. Okay. Is that clear now?
Yes, ma'am.
Yeah. So accuracy, precision, these are the terms we use. Accuracy refers to when there is an exactness, that means when the value determined is exactly same as the one that is expected to be, then you call it as an accurate value. Okay? And precision is a closeness to the measurements. Okay? See, for example, look at this. Like, you have student A, B, C, D given here. They are doing some experiments. So they got these values and this is a mean value. Okay. The true value of a result is 5 grams. The true value is 5 grams. So what can you say about the data given by student 1? 4.98, 4.96 it's not equal to 5. So it's not accurate. But can you see closeness? 4.98 and 4.96 are relatively close. So we call the data as precise. The literal meaning of precise is different from what we use here, students. Okay. So now coming to 4.94, 5.06. Okay. Even the mean value is coming out as 5. See, the first case, the mean value is not 5. 4.97 only. Mean value is 5. So this is accurate. But what is the closeness? 4.94, 5.06, they are, the data is far apart. It's not very close. So we say it's not precise. 5.01, 4.99. The mean value is 5. So what can you tell about this? Mean value is 5. The average is 5. So this is accurate. And how about the relative closeness? 5.01, 4.99. They are very close. So there is a precision. See, this is what they do when you do experiments in the lab. How you're tabulating them. Are the readings close by? All that they will see. Now coming to the last, 4.96, 5.10, and mean is 5.03. So this is neither precise nor accurate. Is that clear? So this will have a total erratic data. It's a total error. Okay. So significant numbers, I hope you're aware of this. So how do you calculate significant numbers? All non-zero digits are significant, right? So look at this, 78 point, all non-zero numbers are significant. So when I say 862.8, 682.5, so how many significant numbers are there?
4.
4. All non-zero digits are significant. Okay. Then second point, zeros preceding the first non-zero number is not significant. So if I put it as, 0.0079. So the zeros preceding the first non-zero number, all these are not significant. So how many significant figures?
2.
2. Only 2. And zeros between two non-zero numbers are significant. Suppose I write like this, 0.00608. What will happen? The first zeros are non-significant, but the zero in between two non-zero, all three are significant. So the number of significant figures will be 3. Clear? Right? And zeros at the end or right of a number are significant, provided they are on the right side of the decimal point, otherwise they are not. For example, I write it as 120. Right side or on the other hand, I write it as 12.0. What's the difference? When I write 12.0, there is a 0.0 I have given here. All three are significant. So the zeros on the extreme right will be significant provided it's on the right side of a decimal point. Whereas when I write 120, the 0 here to the end is not significant. Only 1 and 2 are significant. Is that understandable? Yeah. And counting numbers. Like, when I say 10 pens, 20 pencils, 100 chocolates, okay, all these are counting figures. They have infinite number of zeros. So you can represent that as, infinite number of zeros can be placed after decimal. So they have infinite significant figures. Okay. So that's all about, representing the data, units, and all these things. So I'll directly now go to laws of chemical combination. Mainly we work on that only. So questions also will be asked that way. The laws of chemical combination. So the first law of chemical combination is law of conservation of mass. What is law of conservation of mass? Mass is neither created nor destroyed in a chemical reaction. So it should be very, very precise that you have to, make it that it's a chemical reaction. It's not a universal law. Like law of conservation of energy. This is a law applicable only for chemical reactions, nowhere else. Okay. So mass is neither created nor destroyed in a chemical reaction, or in other words, in a chemical reaction, the total mass is conserved. Total mass of reactants is equal to total mass of products. Okay. So suppose I say magnesium is burning. That's why you must have already learned balancing chemical equations. Why do we balance chemical equation? Why do we balance chemical equation? See, is the equation I've given, is it balanced or unbalanced? So unbalanced chemical equation, we call it as skeletal equation. This is a skeletal equation. Why do we have to balance it? See, when I don't balance it, what will happen? This is 24 grams. This is 32. And this value will be how much? 24 plus 16. This will be 40. Is the mass conserved? Is the mass same?
No.
No. Isn't it? Total mass of reactants is not equal to total mass of products. Right? But when I take a balanced equation, what is balanced equation? 2 mg plus O2 is giving 2 mgO. What is happening in this case? 2 mg, 48 grams, is combining with 32 grams. And here, what will be this? It's 2 into 40, 80 grams. Is the mass conserved?
Yes.
Now? So, when is mass conserved? Only when you're taking a balanced chemical equation. So, why do we have to balance a chemical equation? The contrary? So as to obey law of conservation of mass. Only then law of conservation of mass is obeyed. Otherwise, no. So that's why in any, now henceforth, remember, any numerical you do based on these equations, make sure that you balance. Without balancing, don't take any equation. It's mandatory you balance a chemical equation. A balanced chemical equation is always in consistence with law of conservation of mass. Okay. So law of conservation of mass was put forth by Lavoisier. Sometimes chemists play a role. Questions are possible here or there. I'm telling you, wide scale. Better know the chemists behind this. Next, law of definite proportions. You also call it as fixed proportion or constant proportion also. So this is what I said, it's defining a compound. So a given compound will always contain exactly the same proportion of elements by weight. In other words, a compound consists of atoms taken in a fixed ratio by mass. Isn't that the way we defined a compound? So irrespective of the source you take, so irrespective of water, you take a well water, you take seawater. I mean, seawater, of course, is a mixture. You take well water or you take rain water, or water is obtained in a chemical equation, chemical reaction. Any form of water you take in nature. Everywhere you will find water is H2O and hydrogen to oxygen ratio is 1:8 by mass. Okay. So irrespective, that's what we said. A compound always contains exactly the same proportion of elements by weight. Any form of water you take, it will contain same proportion by weight. Any form of carbon dioxide I take. Carbon dioxide present in atmosphere. Carbon dioxide obtained from automobile exhausts. Carbon dioxide obtained by burning of carbon. Anywhere, any carbon dioxide you take, it's always carbon to oxygen ratio 3:8 by mass. So this is the same thing, the way we define compound, this is what is put forth as law of definite proportion. Okay. Is it clear? In this, I think the law of multiple proportion is missing. I'll explain you what is law of multiple proportion. Let me take you through your textbook once. That file, it is there. Just a minute. Can you see law of multiple proportion given here? The statement. If two elements can combine to form more than one compound, then the mass of one element combining with the fixed mass of the other will always bear a small whole number ratio. What do you mean by this? When two elements can combine to form two or more compounds. See, for example, I have carbon and oxygen. We have, okay? Carbon and oxygen will combine. In one case, it will form carbon dioxide. In the other case, it's forming carbon monoxide. Okay. So, the ratio of the mass of one element that combines with the fixed mass of the other will bear a small whole number ratio. See, what's the ratio of carbon to oxygen in carbon dioxide? 3:8. And this is 3:4. So, fixing mass of carbon as three parts of carbon. So, what is the ratio of oxygen in carbon monoxide as to carbon dioxide? Can you tell me? How much oxygen is there in carbon monoxide, which is combining with 3 parts of carbon? 4 is to oxygen is 8. What is the simplest ratio?
1/2.
1:2. This is what is law of multiple proportions. Okay. So the ratio of the atoms which combines with the fixed mass of the other. So this is important. Whatever we are taking. Is that clear? So let me give you another example. I want you to take N2O, NO, N2O3, NO2, N2O5. Do you know the atomic masses of nitrogen, oxygen? Come on. Basically, you will have to take those weights. What's the total mass of nitrogen, total mass of oxygen in each? So what's the ratio of nitrogen to oxygen? Nitrogen is how much? Nitrogen is 14 and oxygen is 16, right? So how many nitrogens are there in the first?
2, ma'am.
No. Okay. Mass. What's the total mass of nitrogen?
So total mass is 32.
No. And nitrogen alone.
Oh, sorry.
Isn't it 28? 28. So this is a ratio of nitrogen to oxygen now. What is 28 is to? How much is oxygen? 16. Are you able to get that? I'm not asking you the molar mass here. What's the ratio of nitrogen to oxygen? Nitrogen is 28, oxygen is 16. Now, same way in NO, how much is it? It is 14:16. Are you able to understand this, students? So you take the weights of nitrogen and oxygen. How much of nitrogen is there? How much of oxygen is there? You can use the atomic masses. So 28:16 in N2O. 14:16 in NO. And how about this? It's 28:48. Right? NO2, it's 14:32. And last is, it's 28:, how much? 5 into 16. How much is oxygen? Come on, students. What happened? Are you all feeling sleepy?
80.
What is not working?
Come on, say it louder, guys. I heard somebody telling the answer. Come on.
Yeah,
80.
80.
18. Correct. Now, in order to apply this law of multiple proportion, can I apply directly on this? What should I do? Tell me. Yeah, you're nodding your head across. So what should I do? Why can't I apply this directly? So I want to find the ratio of oxygen combining with fixed mass of nitrogen. Okay, I want the ratio of oxygens with fixed mass of nitrogen. So what will be the ratio of oxygen? I want the ratio of oxygen in into O is to NO is to N2O3 is to NO2 is to N2O5. So the mass of nitrogen fixed fundamentally in the first case? No, it is not. See, first case you have 28. In NO it's 14. Again it's third it's 28. NO2 it's 14. That means I have to bring them all on the same platform. So which two are differing? Out of 5, 3 are alike and 2 are differing. So that alone we will change. Is that clear? That alone we will change. We don't have to change the remaining. So I'll make this as 28 is to now. It will be 32. Yes. And NO2 will be 28 is to 64. Now, what is the ratio of oxygen which is combining with fixed mass of nitrogen? That means 28 parts of nitrogen. Now see, how much is it? What will you get? Come on, students. What's the ratio of oxygen now? Where are you hand up, children? What is the ratio of oxygen alone? So, okay, in N2O, how many grams of
Dear students, everybody come on, participate now.
14 is to 16.
yes, in N2O3
28 is to 14.
and NO2?
14 into 32.
14 is to 32 and N2O5 is?
28 into
Is to 80. Correct? Now, what does the law say? Two elements combine to form more than one compound. The mass of one element combining with the fixed mass of the other. So if I take it as it is the mass of nitrogen fixed? Don't
no,
you see
ma'am,
there is, we have 14 is to 16 and 14 is to 32 coming in case of NO and NO2. That means I have to calculate this, making the mass fixed. So let's fix the mass as 28. So what should I do? I'll have to change the ratio again of NO. 14:16. When I double it, it'll become 28:32. Is that clear? Same thing. NO2 is 14:32 will become. What will it become?
28
Double
is
it.
to
28 is
28:64. Now is the mass of nitrogen fixed after changing this
Yes, ma'am.
Yes, ma'am.
throughout?
Yes, ma'am.
Now, keeping 28 grams of nitrogen fixed, what will be the ratio of oxygen? How much oxygen is there in N2O, which is combining with 28 grams of nitrogen? How much is it?
2.
16.
16 is 2. Now in NO
32,
32.
is 2.
64.
Now come to N2O3.
So 48,
48 is 2.
64,
Is 2.
80.
80.
What's the simplest ratio?
1:2:3:4:5.
So when two elements combine to form more than one compound, let's recreate the law. When two elements, nitrogen, oxygen, is combining to form more than one, then it's forming 5 oxides. The ratio of oxygen, which is combining with fixed mass of nitrogen. So the ratio of one element combining with the fixed mass of the other will be a simple whole number ratio. 1:2:3:4:5. Is the law proved? Can you get that now? Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay. So this is something that, when you apply multiple proportions, you have to make sure that you always fix the mass of the other. Okay. Now the next law is Gay-Lussac's law of combining, Gay-Lussac's law of combining volumes. Or it's also called as gaseous volumes. There are two names. You can call it as a combining volume or gaseous volume, anything. So this is about when gases combine in a chemical reaction or when they are produced in a chemical reaction, either way. When they're combining or whenever they are produced, they do so in simple ratio by volume, provided all gases are at the same temperature and pressure. As simple as this. Gases combine. So nitrogen and hydrogen combine to form ammonia. Okay. So when they are combining, so what is happening? Nitrogen gas is combining with hydrogen gas to form ammonia gas. Okay. So gases are combining and gas is also being formed. Ammonia is the gas which is formed in this reaction. So when they combine or whenever the gas is produced in a reaction, they bear a simple whole number ratio by volume. So here we are measuring the volume ratios. That's why this is called as Gay-Lussac's law of combining volumes. So, okay, we have 1 volume of nitrogen combines with 3 volumes of hydrogen to give 2 volumes of ammonia. So what is the ratio, volume ratio of nitrogen to hydrogen to ammonia? What's the volume ratio? 1:3:. Okay. Suppose I take 200 ml of nitrogen. What is the amount of hydrogen needed and what is the amount of, what's the volume of ammonia formed? So what's the ratio of nitrogen to hydrogen, students? 1:3.
1:3.
So if I have 200 ml of nitrogen, then how much of hydrogen will combine in volume?
600.
Yes. And what's the volume of ammonia formed?
400.
400 ml. Is that clear? Are you getting it? This is what is basically your Gay-Lussac's law. You're taking the volume ratio. Believe me, it's only gaseous volume. You cannot take into account liquid volume. Is it clear? See, for example, I take hydrogen is combining with oxygen to form water. Please consider my equation carefully. Okay. So what's the ratio? 2 volumes of hydrogen will combine with 1 volume of oxygen to give 2 volumes of. Is water in the gaseous state or liquid state?
Gaseous state.
Only then I can consider. If it's in liquid state, you cannot consider the volume here. Because liquid volume, it's a gaseous volume what we are measuring, not the liquid volume. Okay. So I'll give you one more equation. Come on. In this case, do it. What's the ratio? So how many volumes? What is CH4 called as?
Methane.
Yeah. So what's the ratio of methane to oxygen now? 1 volume of methane will combine with
2 volumes of
2 volumes of oxygen to give
1 volume of carbon dioxide.
and
2 volumes of water.
do you all agree? Is it right?
Yes, ma'am.
Anybody? Not agreeing with this? Are all agreeing with this?
Yes, ma'am.
What did I say? This is a volume of. So volume of gases. Is water in the gaseous state?
No, ma'am.
Then writing 2 volumes is it's meaningless. Are you getting it? So that's what I was telling you. In case of H2 plus O2 giving H2O, gas, please focus on that. We will take only gaseous volume, not solid or liquid volumes. Got it? Is that clear?
Yes, ma'am.
So take care when it's liquid, especially, the problem will arise with water a lot. So water, see if it is a liquid state or gaseous state. If it is a liquid state, it will not make any contribution towards a volume. Got it? There's a 0 contribution for water as a liquid. All right. Last, Avogadro's law. So it says equal volumes of all gases contain equal number of molecules under same conditions of temperature and pressure. That means if I take temperature and pressure constant, suppose let me take temperature as 300 Kelvin and pressure as say 2 atmospheres. Let me count, let me take 1 liter of hydrogen or 1 liter of oxygen, 1 liter of ammonia. All these are, so what am I doing? I'm taking equal volumes of gases at same temperature and pressure. So the number of molecules, if there are X molecules of hydrogen present, then the same X molecules will be there in oxygen and the same X molecules will be there in ammonia. This is what you mean by equal volumes of all gases contain equal number of molecules. Okay? This is coming from the mole concept. I will explain in the mole concept now that how this is derived. Okay? Is that clear? So when I take STP, what is STP? Standard temperature pressure. What is it? Just now we told. What is temperature? 0 degrees Celsius, 273.15 Kelvin and 1 atmosphere. Then 22.4 liters of hydrogen will contain 6.022 into 10 power 23 molecules. Same 22.4 liters of oxygen will contain same number of molecules. 22.4 liters of ammonia will contain. That means equal volumes of all gases contain equal number of molecules. So this is applicable anywhere, whether you're taking it STP or any other temperature. Equal volumes of all gases will contain equal number of molecules provided the temperature and pressure are kept constant. Okay. Is that clear? Got it?
Yes, ma'am.
I'll take you through this notes because so concept of atomic mass, right? So what is atomic mass? Atomic mass, I hope you know what is an atom and a molecule and all. Atom is the smallest particle of matter which may or may not exist independently. Why did I write may or may not? Why is it may or may not? Which atoms will have independent existence? Which atoms exist independently without combining?
Helium.
Yeah. Okay. Helium belongs to which category?
Noble gases.
Correct. Noble gases. So noble gases. So there are a handful of noble gases. No, what are they? Helium, neon, argon, krypton, xenon, radon. Right? Only these. So they exist in atomic state itself. They don't have to combine. So they exist as atoms. But remaining, leaving these, others will not exist independently. They always combine. So atoms are smallest particle of matter which may or may not have independent existence. Okay. Got it? So atoms, how do you express mass of an atom? You cannot find the mass of a single atom easily. Mass of a single atom is called as absolute mass. Try to catch up the word. Sometimes they say absolute mass of an atom means it's a mass of single atom. Always we take the relative mass. What is relative atomic mass? Relative atomic mass is the ratio. It says how many times the mass of an element is heavier than 1/12 the mass of carbon-12 atom. So your carbon-12 isotope is taken as a reference element for atomic mass. So that's why you call it as a relative. What is the meaning of the word relative? Relative is something that you take on a comparative scale. Basically, you always compare with something. So the mass of the atom is compared with 1/12 the mass of carbon-12. And this 1/12 the mass of carbon-12 is called as 1 atomic mass unit. 1 AMU is 1/12 the mass of carbon-12 atom. Okay. Is it clear? So if I take this relative atomic mass, see here, it's mass of an atom of an element by what? 1/12 is it not AMU? Divided by AMU. And reciprocal of AMU is Avogadro number. Means 1 by AMU is, AMU has a value 1.660 by 10 power minus 24. Okay. When I take a reciprocal of this value is 6.022 into 10 power 23. Is that clear? So, what is Avogadro? This is what is called as the Avogadro number. Avogadro number is a reciprocal of AMU. So, what is relative atomic mass? Mass of an atom by AMU, no? So, isn't it mass of atom multiplied by Avogadro number? Am I right? Multiplied by 6.022 into 10 power 23. Got? Is it clear? So, can I call this as mass of 6.022 into 10 power 23 atoms? Yes or no? What is relative atomic mass? Once again, it's a mass of atom divided by 1/12 the mass of carbon 12. So what is this 1/12 the mass of carbon 12? 1 AM. Okay. And what is reciprocal of AMU? Avogadro number 6.022 and 10 power 23. So when I, reorganize everything, relative atomic mass is mass of an atom divided by AMU, right? And what is 1 by AMU? Avogadro number. So atomic mass can be given as mass of an atom multiplied by Avogadro number. So can I write it as mass of Avogadro number of atoms? See, cost of 1 pencil multiplied by 10. Is it not cost of 10 pencils? Same logic. Mass of 1 atom multiplied by Avogadro number will be mass of Avogadro number of atoms. Can you get that? Are you able to catch up with this? So what is relative atomic mass? It's nothing but mass of Avogadro number of atoms of an element. Got it? And by more often, we express atomic mass as grams per mole. It's unified mass and AMU also we refer, but mostly we use grams per mole. Okay. See, that's what is the difference between mass and atomic mass. Mass is simple, it's grams. Whereas it is grams per mole is the atomic mass or molar mass. So you should be thorough with atomic masses of first. I think I told you about this when I did periodic properties chapter also. 1 to 30 elements. Please keep it as a reference for atomic mass, for atomic number, and the position in periodic table. Clear? You have to keep this in mind. You have to learn this. Be thorough with this. Got it? Is that clear? So 1 to 30 elements atomic mass is mandatory. It's mandatory. You have to. See, atomic mass. How many of you are aware of these atomic masses? Yeah? Yes or no? How many elements you know the atomic masses of? 1 to 20 at least? Yeah? You
Yes,
have to
ma'am.
be thorough students. Otherwise, you will have literally, a struggle in proceeding with this. Don't expect atomic mass to be given in every case. Okay? So gram atom or gram atomic mass is atomic mass expressed in grams. Okay? So when I say 1 gram atom of sodium, see atomic mass of sodium in grams. Clear? Atomic mass of sodium is how much? 23. So 1 gram atom of sodium is 23 grams. 1 gram atom of calcium is 40 grams. That means atomic mass of calcium is 40. That's what you have to remember. Try to, deduce the information from this. And atomic mass, see, I want you to bring the relation. Understand this carefully. So when I take atomic mass or gram atomic mass or gram atom, it will contain what is the mass of this? What is the weight of this? It will weigh atomic mass in grams. Am I right? Clear? Are you able to get the statement? And it will contain how many atoms? Avogadro number of atoms. Please get this very, 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 very clear. Okay. Understood? So let me put this. 1 gram atom of, I have magnesium. So what will be the weight of this? It's equivalent to how many grams? 24 grams is 24 is atomic mass of magnesium. Some time back we did know 24. And how many atoms will it contain? It will contain Avogadro number of atoms of magnesium. It will not contain any other atom. It will contain atoms of magnesium. Is that clear? See, this Avogadro number is something similar to a dozen. So when I say it's a mass of dozen apples, what do you mean? It's that mass which will contain 12 apples, right? Right? When I say dozen apple, it will contain 12 apples. So just like the word dozen, here we are using the Avogadro number. So Avogadro number is quantifying that 6.022 into 10 power 23. That value is what is your Avogadro number. Okay. So 1 gram atom of silicon, it will weigh 28 grams. So how many atoms will it contain? It will contain Avogadro number of atoms of silicon. Are you able to relate this? Got it?
Yes.
Yes, ma'am.
1 gram atom of silver is 108 grams. It will contain Avogadro number of atoms of silver. Mainly you remember 1 to 30 elements. Okay. Got it?
Yes,
Next,
ma'am.
molecular mass. Molecular mass is again same thing. It tells how many times an atom of an element is heavier than, it's heavier than 1/12 the mass of carbon-12 atom. Okay. Is that clear? So this is again the same way, but the best way to find molecular mass is add up the atomic masses. Okay. So here is something I want you to go through the small trick to find the molecular masses. Okay. I'll just take you through the whiteboard. Okay. Can you see the whiteboard, students?
Yes, ma'am.
Yes.
Okay. So the trick here we are using is, this is going to help you a lot in calculating the molecular masses. So when you want to find the molecular masses, I want you to take the masses in units. See, first, fundamentally, you should know the atomic masses from 1 to 30. At least right now, keep the target as 20, day 1. Is it clear? Then memorize the remaining. So it's like, the way you're doing it is take, the atoms in groups as units. See, for example, like I have nitrogen. Okay. Hydrogen. Fundamentally find the, diatomic molecules, O2, N2, Br2. Okay. Bromine is, I'll tell you, bromine, you take it as 80. Then you have Cl2. How much is N2? Quickly. Nitrogen is how much?
14.
I want you to be ready with the atomic masses chart. Is it clear? Tomorrow, when I'm taking your atomic mass, should be ready. You should not take time to, searching for the atomic masses. You have to remember or keep the atomic masses right in front of you. You will have to keep it ready. Only then your calculation will speed up. So how much is nitrogen?
14.
14. So what is N2?
28.
Yes. H2?
2.
2.
O2?
32.
32.
Br2? I gave no. Br is 80. So Br2 is
160.
160.
160. Okay. Cl2?
71.
71. Okay. So now we will just go further. I want CO, CO2, NO2, H2O, Cl2. See the way I'm doing? So what do I do is, the routine way, the way you calculate CO2 is, you probably do it as how much? 12 plus 2 into 16. Isn't this the method you follow? Isn't it? Now, instead of this, the method you're following is already carbon. Okay, carbon oxygen is clear. It's only 2 elements are there. So carbon oxygen will be 12 plus 16. It will be 28. Now, when I take CO2, you start, making it. Isn't it O2 ready? 32. So will this be 12 plus 32? Isn't it easier? Then every time you take it as 12 plus 2 into 16. Next, NO2. What is NO2? 14 plus 32. It's not 2 into 12, 2 into 16 again. You're not going to do that again. Is that clear? Because already the values are ready. So first you organize. First, only the diatomic. Then you take, the next level. Then H2O. H2 is already 2. 2 plus 16. Cl2O. So get out of the regular habit you have. What is Cl2O? It will be 71 plus 32. Isn't it? The calculation is easy. Imagine what you would have done. 2 into 35.5 plus 32. Because already your Cl2 is ready. I'm not waiting for the answers, but I'm asking you to learn the technique. Clear?
Excuse me, ma'am.
Yeah.
O is 16, no, ma'am.
Oh, yeah. I'm sorry. Thank you. Thank you for that. O is 16. Correct. 71 plus 16. Thanks for that. Good. It shows that you're awake very well. Good. Yeah. Thanks for that. It's calculate. Now calculate the values. I'm not, you calculate and keep it ready. So this way, I want you to keep it ready for all the radicals. What is it? Put it for SO3, CO3, SO3, SO2. NO2 is already there here. Then OH, NH2, right? When you do this, it will help you a lot in writing the salts. Is it clear? See, what is CO3? Tell me. I'll give O3 and NH3 also here separately. What is O3? 48. NH3?
17.
Right. Now look at the way we do. So CO3 will be what?
12 plus 48.
Exactly. How much is it? See, to some extent, you have to do addition. You cannot wind up everything. 60.
16.
SO3? Sulfur is 32. 32 plus 48.
80.
SO2? 32 plus 32.
64.
64.
64.
OH, I'll leave it to you. You can do two ways. You can maybe take it as 16 plus 117. Or, isn't it water is 80? How is OH formed? Water minus hydrogen. There are a number of ways you can take it. So the value is 17. NH2?
16.
Yes. Ammonia minus hydrogen. Can you see that? And SO4? 32 plus 64. Now, why I have given you this is, I want you to find calcium carbonate. What will you do? What is the routine method? 40 plus 12 plus 3 into 16. Isn't this the way you used to do? Every time?
Yes, ma'am.
Now, what is the technique we follow? Calcium is 40. Carbonate is how much? 60. How much is it?
100.
Isn't
100.
this much easier? Now tell me, how will you do H2SO4?
2 plus 96.
Exactly. No, now forget the method of expanding everything and writing it. So for that, you should be prepared with, the values of all this, the small units. Is it clear? Of masses. So your job will become very easy. You can calculate the molar masses much way faster. Okay? Clear? So come prepared with this technique. So I'm leaving this technique with you today because tomorrow I'll start with mole concept. This should be in the background. Keep all this ready. Is that clear? So practice some molar masses and come the way we are doing it. Is it clear? Use this technique. Apply this technique to calculate the molar masses. Okay. Okay then. Sir, I think I'll wind up now.